coming to our presentation. I'm Keidai Iiyama, a first-year PhD student in Stanford University. Today, I would like to talk about the autonomous and distributed angles-only navigation and timekeeping in lunar orbit. This research was conducted with Justin Kruger, a PhD student in the Stanford Space Rendezvous Lab under the guidance of Professor D'Amico. First, I would like to start with talking about the motivation of our research. Currently, there is an international interest in building sustainable human presence on the moon. Spacecraft swarm and constellations could be effectively used to support these missions via distributed frameworks. Potential applications include networks of satellites that provide navigation and communication service in lunar regions, such as the LunaNet concept proposed by NASA. Also, these swarms could be used for space situational awareness and space traffic management in cislunar space. Efficient navigation of these swarms and constellations are crucial to achieve these mission goals. To this end, the problem statement of this research is to develop a position, navigation, and timing framework for lunar orbits using only bearing angle measurements from multiple space observers equipped with optical sensors. Using bearing angle measurements has several advantages compared with other methods. First, it requires less frequent contact with the ground stations, since it could be self-contained within the swarm. Because deep space ground stations are limited in number, it is important to rely less on Earth ground stations for scalability. Second, cameras are low size, weight, cost, power sensor with high robustness, accuracy, and dynamic range. There is no need to mount dedicated high-gain GNSS receivers to track weak GNSS silo signals in lunar orbit. Currently, there are dedicated systems both on the ground and in space for tracking space objects with optical sensors, such as UA Space Surveillance Network and SVSS. However, these systems also face several challenges. They are not capable of simultaneously tracking multiple resident space objects and estimating its orbits in near real time with consistently good geometry. They also suffer from large uncertainty because of the small number of measurements available. To overcome these issues, our lab has been developing a novel angles-only navigation framework called ARTMS. ARTMS combines camera measurements and inter-satellite links with multiple observers to achieve autonomous and distributed swarm navigation, including non-cooperative targets. ARTMS could conduct both absolute and relative orbit estimation of the swarm without requiring maneuvers nor frequent ground contact. The architecture will be flight tested in the upcoming Star Fox experiment as part of the Starlink mission. However, when applying ARTMS to lunar orbits, new challenges arise compared with the Earth orbit. First, the gravity potential is weaker and stronger third-body perturbation exists, which could reduce the observability. Second, stable orbit in lunar regions, such as NRHO, are highly elliptical, which has slow-moving and highly perturbated dynamics near the apoplane, which could also reduce observability. Third, we could have less frequent contact with ground stations for clock resets. To this end, the objective and the key contributions of this research is summarized as follows. First, we extend the ARTMS with several developments in the algorithm. We estimate the differential clock offsets and ballistic coefficients as well to improve robustness, and revise fluid dynamics models for accurate state estimation in lunar orbits, and added a new visual-based sensor tracking mode for highly elliptical and constellation orbits. We evaluated the theoretical navigation performance for various orbit and formation types, including low lunar orbit, elliptical lunar frozen orbit, and NRHO. Finally, we validated our algorithm through high-fidelity simulations of ARTMS navigation in lunar orbit using optical simulator with star tracker hardware in the loop. Next, I would like to talk about the architecture of the ARTMS. The algorithm consists of three parts image processing, batch orbit determination, and sequential orbit determination. The details will be explained in the following slides. The objective of image processing, or IMP, is to process camera images and detect targets in images to produce bearing angle measurements. In the IMP, we exploit the knowledge of target kinematics to reduce search space for target tracking. We apply multi-hypothesis techniques to assign the observed bearing angle measurements to each target. In the BOD segment, batches of bearing angle measurements are processed to produce an initial estimate for swarm orbits. To efficiently reach the initial estimate, we sample weakly observable target range, compute the corresponding state estimate for each sample using iterative batch least squares, and choose the candidate state initialization that produces least measurement residuals for the provided IMP angle batches. Finally, the goal of the SOD is to consistently refine swarm orbit estimates using new measurements from the onboard camera and remote observers. In the SOD, we first apply multiple observer assignment algorithms to match corresponding measurements from different remote observers. Next, we perform nonlinear UKF time and measurements updates to produce updated state and covariance estimates. Next, I would like to talk about the updates that we made to the ARTMS framework to enable lunar navigation. First, we added onboard estimation of differential clock offsets and SRP ballistic coefficients for more autonomy and robustness. Clock offsets are propagated in ARTMS using the two-state clock model with frequency random noise and white frequency noise, and assuming the parameters of CSAC microsemi SE.45S. We also estimated the differential ballistic coefficients in the SRP, which becomes relatively important in highly elliptical orbits such as NRHO with weak central gravity. Second, we revised the internal dynamics model for accurate state propagation in lunar orbits. We updated the ARTMS framework so that we could set arbitrary reference frames, central bodies, and third body perturbations. For the gravity model, we used 6x60 for the truth model and 10x10 for the filter model. We considered third body effects from both Earth and Sun in both truth and filter model to make the filter work in three-body problem orbits such as NRHO. Also, we added initial estimation errors to the SRP ballistic coefficients in the filter model. Finally, we implemented a new vision-based sensor target tracking mode for enhanced measurement ability in elliptical orbits and constellation. As shown in the slide, the camera used in the research has the field of view of 12 degrees by 10 degrees. This is not sufficient to track all the satellites in large separation in highly elliptical orbits or different orbital planes without actively changing the attitude of the observer. Therefore, we implemented a new target mode for the observer to point each target in sequence to track all targets in these cases. Next, I would like to present our simulation results. For simulation, we have generated 5 scenarios. The 3 orbits used are the low lunar orbit, elliptical lunar frozen orbit, and the NRHO. For low lunar orbit, 2 types of formations, EI separated and in-train formation was simulated. For the ELFO, an EI separated formation and flower constellation was simulated. The demonstrated functionality and performance of the ARTMS in the simulation is summarized in this slide. The absolute orbit error is around 0.01% to 0.05% in the chief satellite orbit size. The relative orbit estimation error is around 0.01% to 0.3% of the target range. Relative clock estimation error varied from 10 milliseconds to 780 milliseconds, which was all under 1 second. Next, I would like to look deeply into the results of some cases. First, I would like to talk about the swarm in the LLO. As shown in the table, the majority of relative position error occurs in the long track direction. This is due to the weak observability of target range in angles-only navigation. From the figure, we can see that the estimation error experiences periodic growth and shrinkage. Actually, the performance degrades when the chief observer satellite passes through an eclipse and no measurement is available. Despite the performance degrade during the eclipse, the estimation converges robustly in total. The next example I would like to mention is the flower constellation in the ELFO. The most notable feature of this case is that absolute orbit estimation error is much smaller than the formation in a single ELFO orbital plane. This is because ARTMS could exploit larger differences in the orbit perturbations among the satellites to resolve orbit ambiguity. The relative state estimation error degrades compared with the EI formation in a single ELFO, but this is mainly due to the larger target range between the satellites. Actually, the ratio of error to the target range is smaller. In the constellation case, cameras point each target in sequence to track all satellites as we mentioned before. But this is not guaranteed to be optimal in terms of observability. An improvement of this pointing strategy is an important future work. Finally, I would like to show the results of the NRHO case. In the NRHO, absolute orbit estimation error degrades significantly near the apophone. This is due to the smaller relative acceleration between the satellites, which makes the ARTMS harder to resolve the orbit ambiguity. Also, the clock bias estimation errors are larger compared with the LLO case. This is partially due to the long state propagation errors during the SOD propagation. On the contrary, the relative state estimation errors in the NRHO case get larger near the perimeter, as shown in this slide. There are three reasons for this. First, faster motion leads to larger error propagation between measurements. Second, difference between the truth and failure dynamics get larger near the perimeter due to the difference in the order of gravity models. Third, in the NRHO case, target satellites become close to each other in the field of view at the perimeter, which reduces observability. We are working on finding more preferable formations in the NRHO. Here, I would like to summarize the findings of the research. We have proven by simulation in various orbit and formation types that vision-based space navigation are viable means for the Moon. We also made observations on ARTMS performance and limitations. Absolute orbit estimation errors work well when there exists larger difference in the orbit perturbations to resolve orbit ambiguity. Relative estimation error degrades mainly near the perimeter, where there are larger deviations between the truth and failure models, larger error propagation between the measurements, and target becomes close in the field of view. Future generalization and expansions include optimization of the observer's attitude to improve observability, inclusion of the satellite ranging measurements to improve target estimation, and characterization of swarm observability using graph network topologies. Finally, I would like to acknowledge Joshua Sullivan, Adam Cohen, and Toby Bell in the Stanford Rendezvous laboratory to their contribution in the development of the ARTMS software. Thank you for listening to my presentation.